What if the most familiar particle in the universe is not a thing at all, but a storm with a name? What if the solid world, your bones, your desk, the iron core of a planet, rests on a process that never holds the same shape twice? Tonight we go hunting for the proton, and what we find may unsettle the very idea of matter. Hold out your hand. It looks dependable, obedient to weight and warmth, ready for work. Zoom inward in your mind's eye. Skin to cells, cells to molecules, molecules to atoms. We arrive at hydrogen, the simplest, an electron anxious on the outside, and at its heart, a single proton. The narrative we were raised upon says that here, at last, is bedrock, a compact grain, a billiard ball polished by the gods of simplicity. But the story fractures under scrutiny. The proton is not a pebble, it is a play, a choreography of fields, a custody battle of energy, a name we give to stability found in the noise. A proton is built, we say, from 3 valence quarks, 2 up, 1 down, bound by gluons, the carriers of the strong force. The sentence is true enough to teach, and false enough to haunt. For those 3 quarks contribute scarcely any of the proton's mass. Take the sum of their little rest masses, and you will not reach even a 20th of the whole. Where, then, does the rest come from? From motion and tension inside a prison of color, from the kinetic energy of quarks racing within, from the pressure of gluon fields knotting themselves into a storm so dense that mass appears as if by alchemy. The weight of your hand is mostly the weight of motion trapped. Your solidity is the bookkeeping of a perpetual tempest. Look more closely and the boundary dissolves. The inside of a proton is not furniture. It is a crowd. Quarks wink into existence in pairs and vanish again. Gluons split and merge and shuttle color charge like croupiers at a table that never closes. The valence trio are not seated monarchs but persistent accents in a choir. Even the shape refuses to settle. Under gentle probing, the proton looks compact, well-behaved. Under high-energy interrogation it swells, its interior flooding with small X gluons, a fog thickening as you push harder. What is its size if its profile changes whenever you measure it? What is its identity if its contents are a flux? We ask for pictures and are given functions. Deep, inelastic scattering does not show us a portrait, but a probability distribution, a weather map of momentum fractions. The thing we see is a pattern in the spray of aftermaths from violent meetings, the logic of jets and angles and missing energy. We do not photograph a proton, we infer it from debris and trust the symmetries that stitch the inferences together. How many times must a pattern succeed before we grant it reality? Consider the pressure at the proton's core. For an instant, the fields are wound so tight that the inward squeeze rivals even exceeds the imagined violence inside neutron stars. Then, in the next breath of time, the balance reverses. Outward pressure asserts itself, and stability emerges as compromise. Not a stone, not a shell, but a pact. A self that persists because opposing infinities cancel to a sum that endures across billions of years. A proton's measured lifetime is so long that for all practical purposes it does not die. Yet on the timescale of 10 to the minus 24 seconds, its interior lives and dies incessantly. Which tempo defines the real? This is where language begins to limp. We say inside and outside, particle and force, as though the world obeyed our nouns. But the mathematics insists on fields, quark fields carrying color, gluon fields binding them, the whole a gauge invariant tale where proton is the least ambiguous word for an excitation with specific quantum numbers. Electric charge +1, baryon number +1, spin 1/2. The law recognizes the character, even if the cast changes each frame. Perhaps reality is a court of invariance. Perhaps a proton is real because its charges never waver while its innards do nothing but. Press your mind against another peculiarity. Most of the visible mass in the universe, stars, stones, you, does not come from the Higgs field endowing quarks with rest mass. No, it is born in the furnace of the strong interaction. It is the tax levied by confinement, the price of keeping colored things colorless. In this sense, the universe is heavy because the proton is difficult. This is not a metaphor, but a revelation. The cosmos weighs so much not because of stuff, but because of stubbornness. Now, a quiet heresy. What if the proton is not a constituent, but a consequence? What if it is not the brick from which reality is built, but the pattern reality prefers because it is the most stable solution to a deeper, harsher set of equations? If so, then to ask, what is the proton made of, risks missing the point. It may be more useful to ask, what principles force this pattern to appear and persist? We might find, as we did with waves and wind, that a name conceals a process, and the process is the only enduring thing. There are scars in the data that refuse to heal. Measure the proton's charge radius with electrons, and you arrive at one value. Replace the electron with its heavier cousin, the muon, and the proton seems smaller. The discrepancy has narrowed in recent years, but the unease remains. Even the simplest attributes are hostage to the way we pose our questions. Twist the energy, change the distance scale, and the proton answers differently. It is a witness whose testimony depends on the light in the room. Meanwhile, the proton's spin seems to have vanished into the crowd. Quarks do not add up to the whole. Gluons and orbital motion must contribute the rest, and still the accounting is delicate, scheme-dependent, more philosophy than shopping list. You can feel the discipline straining to keep its vocabulary aligned with a storm, and yet no one doubts the proton when a star lights. In the sun's core, protons thread the improbable needle of quantum tunneling to fuse. That quiet defiance of classical odds powers daylight, weather, the chlorophyll that feeds the chain that feeds you. In your body, proton gradients fall across mitochondrial membranes like alpine water, turning nanoscopic turbines that mint the currency of life. We build our civilization on currents of this particle we cannot pin down. It is an odd thing to live by the work of a process and call the process a bead. What then do we mean when we say proton? Perhaps for now this: a durable knot in quantum chromodynamics, an excitation of fields whose symmetries are stricter than our metaphors, a storm that repeats itself so faithfully we have mistaken it for a stone. If that offends common sense, it is only because common sense is parochial, raised on the scales of markets and the weights of doors, not on the pressures that flip sign at the heart of the small. We have opened the door, but before we step through, a harder question waits. If the proton is a storm that our equations name and our measurements constrain, in what sense is it real? What qualifies a pattern to inherit that word? The world will not let us proceed without an answer, or at least a better question. So the next step is not deeper into the atom, but outward into meaning. What counts as real, and who decides? The eye, the instrument, or the invariants that survive them both? What do we mean when we say that something is real? A rock resists your hand, a shadow does not. But by the time we descend to the scales where protons live, the categories begin to blur. Push too hard and you find not pebbles but patterns, not objects but events, that reassemble themselves under the pressure of your questions. The proton sits precisely at that fault line, a creature we can count, accelerate, trap and aim, yet one that dissolves into storms of field when we try to pin it down. If the most reliable constituent of matter is not a thing in the old sense, what exactly earns it the title of real?
Physicists have learned to distrust nouns. The fundamental language of the Standard Model is not beads, but fields. Quark fields with color charge, gluon fields that bind, lepton and gauge fields that mediate. Particles are excitations, bundled ripples, identified by the quantum numbers they carry and the way they endure while moving through the world. But endurance itself is relative. Change the energy at which you interrogate the proton and its contents rearrange. alter the frame of the observer, and even the bookkeeping of quanta can change. If the count of particles depends on who is asking and how, should reality be reserved for what refuses to change when we do?
The more cautious among us answer, look to invariance. A proton announces itself by the charges that never waver: electric charge +1, baryon number +1, spin 1/2, and by the pole it places in the scattering matrix at 938 mega-electron volts, the stable signature of its mass. Whatever roars within, whatever sea of quarks and gluons foams and cancels, the ledger stays balanced. The world knows a proton by the conservation laws it satisfies, the symmetries it respects. In that sense, proton is the name for a stable pattern in a storm, not a marble, but the legal identity of a vortex. And yet there's another kind of evidence that weighs with a human heft. We can do things to protons. We can bend them in magnetic fields and write their deflections into cloud chambers and silicon. We can hurl them around 40-meter rings in hospitals and knife tumors with their Bragg peaks while sparing the flesh beyond. We can whip them to near-light speed, smash them head-on, and use the wreckage to expose the grammar of the forces that shape the world. Ian Hacking once said of electrons, "If you can spray them, they are real." Protons, by that standard, are hard to deny. Whatever our metaphysics, they push back. But the map and the territory continue to argue. In our daily lives, reality is what persists. The table you left yesterday will greet you tomorrow. In quantum field theory, reality may be what is calculable and conserved. The two rarely point to the same picture. Your sense of solidity is built on hydrogen, and hydrogen is abundant almost to the point of farce. By number, the universe is mostly hydrogen atoms, each one a partnership between an electron and a proton. Entire radio maps of our galaxy are drawn from the 21-centimeter whisper of that partnership, a hyperfine flip that depends exquisitely on the proton's magnetic moment. Our cosmic cartography hangs quite literally on the character of this storm. It would be perverse to call it unreal. Even so, the proton wriggles in the grip. Ask for its size and you will provoke a quarrel between methods. Probe it with electrons and you measure one radius. Replace the electron with a muon orbiting much closer to the proton's heart, and you infer a different one. The tension has softened with improved experiments, but it has not evaporated. Ask for its spin, and you enter a morality play about responsibility. The valence quarks do not carry enough. Gluons and orbital motion must shoulder the rest, and the sum depends on how you partition the bookkeeping. If reality were a photograph, this would be grounds for doubt. But reality at the small does not sit for portraits. It tolerates only sums that survive translation. So we try other tests. We look for what refuses to negotiate. The proton's charges do not drift. Its mass hides behind renormalization schemes and the trace of the energy-momentum tensor, but its resonance in scattering remains nailed to the same number within experimental mercy. Its role in chemistry is tyrannical. Hydrogen's single proton sets the tone for bonds, acidity, the architecture of molecules. The periodic table is the family tree of proton count. In stars, protons tunnel and fuse against classical odds, their stubbornness the first act of the chain that powers the sky. In biology, proton gradients fall across membranes, driving rotary machines that purchase life from entropy. These are not metaphors, they are instructions for a universe that works. If you require reality to do work, the proton is overqualified. Still, a whisper intrudes. Perhaps usefulness is not the same as being. Perhaps the proton's reality is conditional, a nickname for a QCD solution that happens for now to be globally available. Consider density so crushing that atoms die, electrons pressed into protons until neutron matter absorbs them both. Consider temperatures so obscene that confinement melts and quarks run free for a window of cosmic time. In these theaters, the identity of protons blurs into phases with different rules. Are we then to say that the proton was never real? Or do we say that reality, like weather, keeps seasons, and that our word names the season in which we live. Another retort answers with modesty. Reality is what is there when you are not looking and what comes back when you try again. By that measure, the proton excels. We trap single protons for months in electromagnetic bottles, weigh their magnetic moments to parts per billion, compare them to antiprotons, and find the symmetries of the world holding like steel. Such obstinacy is not the behavior of fiction, and yet the inside remains a negotiation of scales and schemes, a play of distributions that shift as you alter the energy of your gaze. The mind itches. What kind of thing has an outside that overrules the chaos of its inside?
Perhaps we have been trained by the wrong metaphors. The question, what is a proton, presumes there is something to point to, an inventory to list, a diagram to shade. But the proton may be less like a stone and more like a melody, less a lump and more a law obeyed locally. A melody is real enough, it can move the world. But it is also pattern, contingent on medium and frame. You cannot pour it into a jar, you can repeat it until it is yours. When physicists say the proton is an excitation of a field with quantum numbers q, b, j, they may be saying, here is a melody so robust that matter itself is its echo.
This is not an escape into poetry, it is a proposed criterion. In a world described by fields, the right to be called real belongs to those patterns that remain when methods change and frames rotate. What survives from the instrument to the cosmos, from the lab to the star, the proton's invariants do, its particulars do not. That is uncomfortable because we love particulars, but discomfort has often been the fee for admission to truth.
So we have options. We can be entity realists and insist that the proton is as real as the things it lets us make and break. We can be structural realists and say that what is real are the relationships, the symmetries, the conserved numbers, the S-matrix poles, and that proton is shorthand for a certain cluster of them. Or we can be pragmatists and note that these distinctions fade when the machine turns on and the beam arrives. Reality is what lets the beam do what the equations forecast and what the detectors count.
You may feel the ground tilt underfoot. Good. The next step requires steady feet. Definitions are not enough. They must be earned. The only way to settle what counts as real in physics is to follow the chain of evidence, the experiments that exposed the nucleus as hard, the collisions that resolved partons within, the measurements that forced us from marbles to fields. Words will not decide, data will. We began by asking what makes the proton real. Perhaps the better question is, how did we come to recognize the proton in the first place, and what did the world have to become for that recognition to hold? The answer lies on a path lit by scattered alpha particles and showers of debris in high-energy halls. If reality is a ledger of symmetries and results, the entries were written by beams and plates and eyes that learned to trust the unexpected. Shall we read the first pages? Imagine a sheet of gold so thin it trembles at your breath. Now fire alpha particles, helium nuclei, straight at it, and expect, as classical sense demands, that they'll drift through with only the gentlest nudge. In 1909, Geiger and Marsden watched instead as a few projectiles bounced almost straight back, ricocheting as though they had struck a wall. Ernest Rutherford, who set the trap, grasped the enormity at once. To rebound a heavy, fast particle, the atom must hide a tiny, massive core. He likened the surprise to firing a shell at tissue paper and having it return. In a world that thought matter was pudding studded with raisins of charge, the nucleus stepped out from behind the curtain. Solidity had been pushed inward. What Rutherford had caught was not yet the proton, but the stage on which the proton would stand. Between 1919 and 1920, in a series of transmutation experiments, he knocked nitrogen until it gave up something familiar, hydrogen nuclei torn from heavier atoms. If hydrogen carried a single positive charge and sat at the base of the periodic table, perhaps its nucleus was the fundamental positive unit from which other nuclei were built. He named it the proton. A name is not proof, but it can be permission. to look for laws that make the name deserved. The early decades that followed learned to steer charged particles like script across detectors. Cloud chambers traced their paths in fog. Later, bubble chambers etched them in boiling strings of pearls. Tracks curled under magnetic fields, and from their arcs we read momenta as one reads a melody from a score. The proton, invisible in itself, could be counted by the geometry it impressed upon space. Already a theme whispered, "We do not see particles, we see the world obey them." The hydrogen atom turned into a yardstick. Spectroscopy, lines of light at frequencies so precise they could shame a metronome, revealed how the electron and proton talk to each other across the gulf of the atom. Tiny splittings in those lines, hyperfine structures, betrayed the proton's magnetic moment and, with it, hints of its extent. If the proton were truly point-like, some details would be different. It isn't. The atom said so. A deeper microscope arrived when electrons ceased to be merely companions in atoms and became probing beams. Robert Hofstadter in the 1950s drove electrons into protons and neutrons and measured how the scattering angles deviated from what a point would demand. From those deviations, encoded in form factors, the fingerprints of extended charge, he inferred a size, a charge distribution smeared across about 0.8 femtometers. Not an indivisible speck, but a compact, structured object. This was not a photograph, it was a negotiation. Electrons asked questions by imparting momentum, the proton answered by flexing. In that flex lay a radius, a shape that depended on how you pressed. But if Hofstadter's electrons felt a smooth, spread-out charge, another generation of beams would find grit beneath the polish. In the late 1960s at SLAC, electrons were hurled into protons with energies sufficient to shatter the pretense of a continuous interior. The scattering was deep and inelastic, deep because the momentum transfer probed very short distances, inelastic because the proton did not survive intact. Instead, the wreckage spilled into sprays of hadrons. Out of the distributions of those sprays emerged a startling regularity, Bjorken scaling, a pattern that said the electron had struck point-like constituents inside the proton that carried fixed fractions of its momentum. Richard Feynman called them Protons. Murray Gell-Mann had already proposed quarks. The pieces began to agree on a language. What the experiment saw was not a trio of marbles in a bag, but a hierarchy of structure. A few persistent carriers of momentum, the valence quarks, and a sea of transient quark-antiquark pairs and gluons, all jostling and sharing. A proton presented to the electron a map of probabilities. At any given instant, the chance of finding a constituent with a particular fraction of the proton's motion. It was a weather report, not a census. Yet it was repeatable, predictive, indifferent to our longing for pictures. Ask the same question with the same energy, and the same storm pattern would reappear on the detector's shore. Another surprise, as the energy climbed and the resolution sharpened, the interior grew crowded. The parton distributions swelled at small momentum fractions. Gluons multiplied like foam in a wind-whipped sea. The more insistently you asked for point-like truth, the more the proton answered with a fog of fields. Simultaneously, the strength of the strong force softened at short distances, an effect later baptized asymptotic freedom, hinting at a theory, quantum chromodynamics, in which colored charges could dance nearly free when pressed hard, only to be bound ever tighter as they tried to leave. Confinement would be the tax for color. Hadrons, including protons, the evasions the theory allowed. In that arc, from gold foil to deep inelastic scattering, protons changed from the hard kernels of Rutherford's nucleus to processual knots in a field theory. The evidence was a chain, deflections, angles, cross-sections, scaling curves. Each link did not so much show a proton as constrain the space of stories we could tell about what a proton must be. Reality tightened its grip without ever offering a face. Even the accelerators themselves became arguments. The first split atom in 1932, Cockcroft and Walton driving protons into lithium, was not simply proof of technical bravura. It was the world admitting, under the right push, to transmutation by proton hammer. Later, rings grew vast. Synchrotrons herded protons to energies unimaginable at Rutherford's bench, and when protons struck protons, the resulting jets betrayed the underlying partons with clean, collimated signatures. By this point, the community had learned to trust patterns in debris more than daydreams about little beads. We became, in a strict sense, reconstructionists. We read ruins. Yet for all this triumph, trouble kept pace. Measurements of form factors with different techniques refused to lie neatly together. Some seemed to prefer a dipole fall-off, others insisted on deviations. Proton structure functions, those Parton weather maps, shifted with the energy scale at which you asked, and although the theory prescribed how they must shift, the philosophical itch remained. If the answer slides as you move the ruler, what exactly is the thing we claim to be measuring? It is here that the proton story demands a cooler patience. You can, with discipline, reconcile the scale dependence by accepting that structure at the quantum level is not a photograph but a family of conditional statements. If you interrogate at momentum q, the distributions are thus. If at q prime, they are otherwise, and a renormalization group will carry you from one to the other. You can, with equal discipline, accept that what is invariant under these transformations, the charges, the pole in the scattering matrix, the tapestry of symmetries, deserves the name proton more than any drawing of an inside. But one can forgive a listener for wanting at least one number to hold still. Which brings us to the number that would not, the proton's radius. The electron scattering community settled on a value emerging from decades of careful work. Then, muonic hydrogen, an exotic atom in which a muon orbits so close to the proton that its energy levels are exquisitely sensitive to the proton's charge distribution, reported a significantly smaller size. The so-called proton radius puzzle rattled constants and careers. Was there new physics at play? Or had we learned again that the meaning of a simple question depends perilously on how you ask it? We have followed the path from the first recoil of alpha particles to the partonic weather inside a shattered proton, and the pattern that emerges is both bracing and humbling. Every advance has replaced an image with an inference, a picture with a principle. We have learned to trust what repeats under translation. But even in this hard-won sobriety, the proton refuses to sit still. If the very notion of how big a proton is can change with the instrument that inquires, what other certainties are waiting to slide when we turn the knob? The story of the proton, so confident in its experimental foundations, began to tremble on the edge of a decimal place. For decades, electron scattering and hydrogen spectroscopy had converged on a comfortable picture. The proton's charge distribution smears across about 0.88 femtometers. Not a number one can imagine in the ordinary sense, 10,000 times smaller than the atom it anchors, but a value written into textbooks and trusted by the builders of constants. Then came the muon. Muons are heavy cousins of the electron, sharing the same negative charge but 200 times the mass. In hydrogen, replace the electron with a muon, and its orbit shrinks inward, hugging the proton so tightly that its energy levels become exquisitely sensitive to the proton's size. In 2010, an experiment at the Paul Scherrer Institute used this exotic atom, muonic hydrogen, to measure the proton's radius. The result landed like a thunderclap, 0.84 femtometers, smaller by 4%, but enough to rattle the scaffolding of quantum electrodynamics, to unseat Constant's thought secure, and to leave us wondering if our definition of the proton had slipped out from under us. This was no trivial discrepancy. In physics, a 0.5% divergence between methods can be tolerated, patched by systematics. A 4% mismatch is a rebellion. It threatened the Rydberg constant, the yardstick of atomic physics. It stirred whispers of new forces that might couple differently to muons than to electrons, a crack that could point toward physics beyond the standard model. For a time, the so-called proton radius puzzle was a riddle without an answer, a phantom flaw that made one of our most trusted particles look unstable in its own portrait. The community split. Some turned suspicion on the mnemonic measurements. Was there an overlooked correction, a subtle shift in vacuum polarization or Lamb shift calculations? Others doubted the electron data, reanalyzing decades of scattering results and atomic transitions. Still, others dreamed boldly, proposing new bosons, leptoquarks, hidden interactions that might distinguish between families of leptons. For each, the proton was no longer a stable pedestal, but a trembling question mark. How big is it really? Follow-up experiments multiplied. New electron scattering campaigns sharpened their precision. Laser spectroscopy of regular hydrogen tried to close the gap with techniques matching the muonic accuracy. Some results leaned toward the smaller radius, others clung to the old. For years, the field was caught in suspense, watching as decimals moved and error bars shrank, waiting for the two portraits to reconcile or to explode into contradiction. What is unnerving is not only the radius itself, but what it represents. When we speak of the size of a proton, we are already compromising with language. The charge radius is not a wall, but a slope, the rate at which the proton's electric form factor falls with momentum transfer. It is an extrapolation, not a ruler laid across. To change it is to change our understanding of how charge diffuses within the storm of quarks and gluons. To change it is to admit that our picture of the proton is hostage to the questions we ask, the particles we use as interrogators. If the proton's radius is not a single value but a dialogue between probe and probed, what then is its reality? Is there an essence or only context? Does a proton have a size independent of the way we measure it, or is its size precisely the family of answers that different methods provide? The radius puzzle, softened but not slain, leaves behind a deeper unease. It tells us that the proton is not a finished concept. It is an invitation to humility. The particle we thought we knew best can still disobey, can still mock our constants, can still force us to consider that real might mean something other than what fits comfortably in the margins of a textbook. And if the proton resists even our simplest questions, what is your size? What is your spin? What are you made of? How many of our assumptions about matter rest on shifting ground? If the most familiar nucleus still holds secrets, what does that say about the universe built upon it? For generations, physics painted the proton as simple. 3 quarks bound by gluons, whirling together to make up its mass, its charge, and its spin. Spin, in the quantum sense, is not rotation in space, but an intrinsic angular momentum, a deep identity tag carried by all particles. The proton's spin is 1/2, a neat fraction, an anchor in the standard model. The story seemed closed. Add up the spins of the 3 constituent quarks, and you should get 1/2. But in 1987, the European muon collaboration cracked that confidence. By firing polarized muons into polarized protons, they probed how quarks align inside. The result was staggering. The quarks' spins seemed to contribute only a small fraction, maybe 20 to 30% of the proton's total spin. The neat arithmetic collapsed. The proton's spin, one of its defining properties, did not come from where we thought. The shock rippled through physics as the proton spin crisis. If not quark spins, then what? Possibilities emerged. Perhaps gluons, the force carriers binding quarks, carry spin that contributes. Perhaps orbital angular momentum, quarks and gluons not just spinning but swirling around each other, fills the gap. Suddenly the proton was no longer a tidy trio, but a seething democracy of motion, where even empty space inside contributed to its angular identity. Experiments rose to the challenge. At CELEST, at Brookhaven's relativistic heavy ion collider, at CERN's compass experiment, polarized beams and targets interrogated the hidden spin structure. Some data suggested gluons play a large role, then others narrowed it, hinting their contribution is modest. Orbital motion, the dance of quarks and gluons, became harder to pin down, but increasingly likely to be essential. What was once thought a settled ledger is now a mystery of bookkeeping. The spin crisis was not just about adding numbers, it was about the very ontology of the proton. Does a proton have spin as a single entity, or is its spin the emergent sum of countless restless motions within? The crisis revealed that protons, like people, are more than the sum of their parts. Their essence is not static, but dynamic, born of constant exchange. For philosophers of science, the lesson cut deep. A proton is not an object in the classical sense, but a process, a storm whose average behaviors give the illusion of solidity. Its spin, once thought intrinsic, is a compromise between quarks, gluons and orbital currents, a compromise that only holds when viewed from far away. The crisis is not over. Modern lattice QCD simulations, vast computations modeling quarks and gluons on supercomputers, still wrestle to reproduce the proton's spin. Incremental progress has been made, yes, but the fact remains. One of the most fundamental properties of the proton cannot yet be fully explained from first principles. This is not a failure, it is a revelation. It tells us that the proton is not primitive but profound, a crucible where our theories are stress-tested to their breaking point. It tells us that reality, even at its bedrock, resists easy definition. And it raises a chilling question. If we cannot explain the spin of a proton, how secure are we in explaining the universe it composes? And so, the spin crisis stands as a reminder. Even the smallest things conceal infinities. Even the proton, foundation of atoms, is a riddle still unfolding. Which forces within it whisper the truth, and which forces still wait to be discovered? To imagine a proton is to invite paradox. Textbooks describe it as three quarks bound tightly by gluons, a simple, orderly picture. But the deeper physicists looked, the stranger it became. Inside the proton lies not a clean architecture, but a teeming ocean, a sea of ephemeral quark-antiquark pairs flashing in and out of existence. The very structure of matter turns out not to be a skeleton of certainties, but a restless surf of possibilities. The existence of this sea was not just theory, it was forced upon us by evidence. Experiments probing protons with high-energy electrons in the late 20th century revealed more activity than the three-quark model could explain, particles scattered in ways that betrayed the presence of unseen actors. The proton was not a static shell, it was a dynamic environment. Where do these extra quarks come from? The answer lies in the strange nature of the strong force. Gluons, which bind the proton together, carry energy. And in quantum field theory, energy begets matter. Gluons can split, briefly creating a quark-antiquark pair before annihilating again. This constant bubbling makes the proton far more complex than its iconic diagram suggests. It is a churning maelstrom in which three valence quarks are merely anchors in a storm of fleeting companions. This realization shattered the once comfortable notion of permanence. The three quarks we were taught about are not always the same three. At any moment, a proton contains a fluctuating census of matter and antimatter, woven from the fabric of the quantum vacuum itself. What we call a proton is not a thing at all, but a process sustained by motion and exchange. And then came the asymmetries. If quark-antiquark pairs flicker into being randomly, one might expect a balance, equal numbers of up quarks and down quarks, equal behaviors from each. But measurements showed otherwise. In 1991, the new muon collaboration discovered that there are more anti-down quarks than anti-up quarks in the proton sea. The imbalance defied naive expectation. Why would the vacuum itself favor one flavor over another? Theorists scrambled. Some invoked pion clouds, virtual mesons surrounding the proton that bias the fluctuations. Others look to deeper QCD effects, suggesting that the gluon field is not impartial but biased by the symmetries of the strong interaction. The proton sea, once assumed to be featureless foam, turned out to have currents and tides. This is the break into two moment for our story, the turning point where the proton ceases to be simple at all. We leave behind the child's sketch of three particles in a circle. We enter a domain where the proton is alive with restless creation, where forces and fluctuations shape even its identity. For physicists, the implications are profound. If protons are not simple, then predictions about nuclear structure, star formation, and even the birth of the universe itself must be reconsidered with care. The stability of the atom rests on this boiling chaos, yet somehow the chaos sustains stability. Out of turbulence comes order, as if the universe has mastered a paradox that we have not. And for philosophers, the questions deepen. What does it mean to call something real if its parts cannot be counted, if its contents are transient, if its form is an emergent average of seething fluctuations? The proton becomes not just a particle but a metaphor, a reminder that stability may be born from perpetual change. The sea also poses a hauntingly practical question. If we have not yet mapped the proton's full population, how can we say we truly understand matter? Today, global collaborations like the Electron-Ion Collider under construction in the United States are preparing to chart this inner ocean with unprecedented precision. They aim to illuminate the gluon distributions, to weigh the tides of the sea quarks, and to map the proton not as a cartoon but as a living entity. The stakes are high. For beyond the scientific curiosity lies the recognition that the proton sea may hold the key to phenomena we barely grasp. The matter-antimatter asymmetry of the universe, the stability of neutron stars, the mechanisms that gave rise to visible matter at all. And so we stand at the edge of this inner ocean, peering into the foam. We know it is there. We know it is restless, asymmetric, and alive. But we do not yet know its laws. The break has been made. The proton is no longer the proton we thought. It is not merely three quarks. It is a sea, a storm, a complexity. The question becomes inescapable. If the proton is not what we thought, then how far down does the deception go? How much of reality is built on shifting seas we have not yet charted? Every story has a secondary thread, a quieter current that runs beneath the main river. In the tale of the proton, this B story is not about quarks or gluons alone, but about the scientists themselves, their relentless struggle to extract truth from shadows. If the A story is the proton's anatomy, the B story is our confrontation with the limits of perception. The human mind yearns for clarity, but the proton resists it. Imagine peering into a house through frosted glass. You glimpse shapes, motions, suggestions, but never the full detail. That is how physicists have studied protons, by hurling particles at them, catching fragments, and reconstructing a scene that forever refuses to settle. The proton reveals itself not directly, but through echoes, trails, and distortions. Consider deep, inelastic scattering, the tool that cracked open the proton in the 1960s. High-energy electrons fired at protons did not bounce off smoothly, as if from a billiard ball. They splintered, producing scattering patterns that implied substructure. Yet the data were messy, ambiguous, and open to interpretation. In those collisions, physicists glimpsed something within, but never saw it with naked certainty. The proton was like a figure glimpsed in fog, real yet elusive. This difficulty gave rise to a deeper philosophical question. Can we ever say with confidence what a proton is? Or are we forever confined to models, metaphors, and probabilities? The proton becomes a mirror, forcing us to confront not just its mystery, but our own. We crave definitive outlines, but the universe seems woven from approximation. The B story also unfolds in the tension between simplicity and complexity. Early models sought elegance, 3 quarks, cleanly bound. The mathematics was manageable, the diagrams neat. But reality disobeyed. Data pointed to seas of quark-antiquark pairs, to shifting distributions, to gluon self-interactions. The picture grew wild, almost chaotic. Scientists faced a dilemma: abandon simplicity and embrace complexity, or force nature into a box too small for its truths. Some resisted. For decades, debates raged in conference halls and journal pages. Was the proton a fixed structure or a statistical haze? Could the Standard Model truly contain its storms? This human drama, the pride, the doubt, the stubbornness, became inseparable from the science itself. Knowledge advances not by perfect consensus, but by relentless confrontation, by the clash of competing visions. In this struggle, new tools emerged. Particle colliders grew in power, probing protons with energies that mimicked the universe's first instance. Computers, once too weak to handle quantum chromodynamics, evolved into supercomputers capable of lattice simulations. Slowly, the fog began to thin. Yet even now, every glimpse into the proton seems to reveal not finality, but deeper complexity. The closer we look, the stranger it becomes. This is the B story, not the proton itself, but our dance with its shadows. It is the human arc that parallels the proton's arc. As we descend into the mysteries of its structure, we also descend into the limits of our tools, our language, and our very capacity to know. And perhaps this is the more unsettling revelation. The proton may not be unreal in itself. It may be our comprehension that is fragile. What if protons are perfectly real, but only in ways that human cognition cannot fully grasp? What if we are creatures built of processes too alien to ever map completely? In this shadowed mirror, the scientist becomes both hero and wanderer. Every collision experiment, every simulation, every scattering pattern is another torch held aloft in a cave whose walls recede endlessly. The more light we shine, the more darkness we uncover. And yet, driven by the need to know, we continue. This narrative parallel, the proton's evasive reality and our own uncertain quest, sets the stage for the ordeal to come. For if the proton is not what we imagined, and if our tools cannot give us certainty, then what happens when we confront the full scope of its contradictions? The B story is not a distraction, it is the heart. Because in asking whether protons are real, we are truly asking whether our perception of reality itself can ever be trusted. The shadows grow longer, the stakes higher. Ahead lies the ordeal, where the proton's contradictions sharpen into a crisis. If protons are not real in the way we imagine them, then what becomes of everything built upon them? Every great journey meets its darkest hour. For the story of the proton, this ordeal arrives when certainty itself begins to fracture. The question is no longer whether the proton is complex. That much is clear. The crisis is whether the proton, as we imagine it, is real at all. Let us begin with a paradox that refuses to be ignored. The proton is stable, yet it should not be. According to the most widely accepted formulations of particle physics, protons ought to decay, slowly, yes, over vast spans of time, but inevitably. Grand unified theories, ambitious frameworks that attempt to merge the strong, weak, and electromagnetic forces predict proton decay as a natural consequence. Yet experiments searching for this phenomenon, Super Kamiokande in Japan, among others, have seen nothing. Billions of tons of water, watched for decades, have not yielded a single confirmed event. This silence is both reassuring and terrifying. On one hand, it affirms the proton's stability. The atoms in your body, the matter of the earth, the fabric of stars, all endure. On the other hand, it reveals a mismatch between theory and reality. If protons do not decay as expected, then either the theories are wrong, or our understanding of the proton itself is incomplete. The ordeal tightens. A particle so familiar is now a riddle that defies even our best equations. Then comes the radius puzzle. Measurements of the proton size, its charge radius, should converge neatly, yet they do not. Experiments using electrons gave one value, while those using muons gave another, smaller figure. The discrepancy was tiny in absolute terms, but enormous in significance, enough to cast doubt on precision quantum electrodynamics itself. Was the proton larger, smaller, or something subtler still? Was the very act of measurement reshaping the result? Once again, a crack appeared in the foundation, and cracks multiply. The proton's mass, for instance, does not come primarily from the mass of its quarks. Add the quarks' intrinsic weights, and you get only a fraction, barely 5% of the whole. The rest seems to arise from gluonic fields, virtual particles, and the restless churn of the quantum vacuum. In other words, the proton's mass is less a sum of parts than an emergent storm, a resonance born of activity rather than substance. How then do we call the proton real? If its identity arises not from what it is, but from what it does, are we dealing with a particle or with a process? This ordeal is philosophical as much as scientific. The proton has been our rock, our protos, the first thing, the given. But as we dig deeper, it behaves less like an object and more like a shifting cloud of probabilities bound together by equations that we ourselves cannot solve completely. When reality's anchor turns liquid, what is left to hold on to? Even the very notion of individuality dissolves under scrutiny. In high-energy collisions, protons splinter into showers of mesons and gluons, ephemeral sprays of matter that defy neat categorization. The proton's identity seems not intrinsic but contextual. It is a proton when whole, but a burst of other particles when struck. This is not stability but transformation, not essence but behavior. The ordeal presses us further. Perhaps the proton does not exist as a singular thing, but as a momentary configuration in a deeper, ceaseless flux. Here, humanity's dependence on the proton sharpens the tension. Our bodies, our world, our stars all rely on its apparent solidity. Yet in the laboratory, it slips away into ambiguity. Are we built on foundations or illusions? If the proton cannot be fully trusted as real, then what of atoms, molecules, and everything that follows? The ordeal becomes existential. Physicists feel this pressure keenly. For decades, the Standard Model has provided predictive power of astonishing accuracy. But it rests uneasily on the unresolved mysteries of the proton. Experiments strain to reconcile conflicting results, while theorists struggle with equations that may never yield closed solutions. The crisis is not failure but confrontation. We must admit that one of nature's most common particles remains, in crucial respects, unknowable. And this is where the ordeal bites deepest. The proton, once thought of as matter's building block, now appears less like a brick and more like a whirlpool, real enough to grasp, yet impossible to pin down. An emergent pattern in the quantum sea, flickering, dynamic, context-dependent. For the viewer, for the seeker, this is the darkest point of the arc. The question looms not just over physics, but over reality itself. If protons are not real in the ordinary sense, then perhaps nothing is. Perhaps all we call solid is but a veneer of patterns, stabilized by forces we do not fully understand, destined one day to dissolve back into the void. And yet, in every ordeal lies the seed of transformation. To see the cracks is not to lose the foundation, but to glimpse a deeper one, hidden still. For even if the proton is not real in the way we imagined, what new reality might it point us toward? That is the question waiting on the other side of this darkness, and it is the question that will define the next turn of our journey. Out of the ordeal, when certainty shatters, there is always a reward. For the seeker of protons, the reward is not a neat resolution, but a deeper glimpse into truth, one that reshapes our conception of reality. If the proton is elusive, unstable in definition, impossible to capture in a single equation, then what it grants us in return is the humbling recognition that reality itself is more layered, more astonishing than we dared to believe. Let us begin with the revelation of emergence. When we learned that the proton's mass is not the sum of its quarks, but an emergent property of gluonic fields and quantum fluctuations, we glimpsed a profound shift. Solidity arises not from matter, but from energy in motion. 95% of the proton's mass, the weight of your body, the heft of the Earth, the density of stars, comes not from intrinsic particles, but from the storm of interactions within. The proton rewards us with an existential reversal. Reality is not built on things, but on processes, dances of fields and forces too restless to ever be still. Another reward lies in the sheer precision of what we do know. Despite the proton's complexities, the Standard Model predicts its behaviors with uncanny accuracy in many contexts. Theorists can calculate scattering cross-sections, magnetic moments, and decay channels with exquisite precision, often matching experiments to a dozen decimal places. This alignment between human equations and natural outcomes is its own reward, proof that even in the fog we are tracing patterns woven into the cosmos itself. If the proton is a storm, then it is a storm whose winds obey laws, laws we can map, laws that anchor us even amid mystery. Then comes the reward of unity. The proton embodies the strong force, the mightiest of nature's interactions, and in so doing, it links us back to the birth of the universe. In the first millionths of a second after the Big Bang, protons and neutrons froze out of quark-gluon plasma, seeds of the matter that would form galaxies. To study the proton is to touch that origin, to trace our lineage back not just to stars, but to the very instant the universe began to take form. It rewards us with continuity. Your body, this world, the cosmos itself, all echo the same binding forces at the proton's core. The proton also rewards us with humility. Every anomaly, the radius puzzle, the spin crisis, the mass mystery, forces us to question assumptions and refine our models. These are not failures but compass points, guiding us toward new physics. Perhaps beyond the Standard Model lies a truer account, one in which the proton is not a puzzle but a revelation. Dark matter, dark energy, unification. These grand mysteries may all depend on insights that protons hold locked within. Their resistance to explanation is not obstruction but invitation, and the greatest reward is perspective. The proton, unseen by the naked eye, smaller than imagination can comfortably hold, is the key to everything that is. To meditate on its mysteries is to realize how fragile our certainty is, how provisional our knowledge remains, and how vast the unknown still stretches before us. This perspective rewards us not with answers, but with awe. There is another layer of reward too, an almost spiritual one. In discovering that the proton is not an object but a process, we are reminded of ourselves. Are we too not processes? Our bodies are not fixed but flows of matter and energy. Our thoughts not objects but currents. Our lives not static but stories unfolding. The proton reflects us, impermanent, dynamic, real, not in its solidity but in its ceaseless becoming. From the ordeal, the proton emerges not as diminished but as magnified. It is not just a particle but a window into the structure of being itself. The fact that it defies simple description is precisely why it matters. In its contradictions, it reveals that reality is stranger, deeper, more alive than our categories can contain. This is the proton's gift. The reward for looking closely is not closure but wonder. It whispers that reality does not flatten into equations but expands into mystery, that knowledge is not an end but a beginning, and that even the most ordinary particle is a gateway to the extraordinary. Yet this reward carries weight. To glimpse deeper truths is also to feel the burden of what remains unanswered. If the proton is an emergent storm, then what deeper laws govern the storm itself? If its stability contradicts theory, what does that say about the ultimate fate of matter? If its mass is born of motion,
What does that say about the fabric of existence?
The reward is never free. It opens doors, but behind each door lies another question. And so, as we stand in awe before the Protons' revelations, we must also ask, what comes next? Because the journey is not done. The Proton has given us wonder, but wonder is only the beginning of transformation. Ahead lies the road back, the challenge of integrating these revelations into a coherent vision of reality, a vision that does not merely describe the Proton but redefines our place within the universe itself. The reward of revelation, the awe of seeing the Proton not as a particle but as a process, cannot be the end of the journey. For the seeker, the next step is the road back, the long, difficult task of stitching these discoveries into a broader understanding of reality. It is one thing to marvel at the mystery of the Proton. It is another to live with it, to integrate it into the map of the cosmos and into our own conception of existence. This road is paved with contradictions. On one side lies the Standard Model, physics' most triumphant theory, capable of predicting particle interactions with almost uncanny precision. On the other side lies the Proton itself, stubbornly refusing to fit neatly within those predictions. The Proton's radius puzzle still lingers, a rift between experimental results that refuses to close. The Proton's spin remains unsettled, its origins dispersed among quarks, gluons, and orbital motion in ways we cannot yet quantify. Its mass, drawn almost entirely from the chaos of quantum chromodynamics, remains a demonstration of emergence that our equations can only approximate, never fully resolve. The road back requires that we carry these contradictions not as defeats, but as signposts. They tell us that our framework, while powerful, is not final. They tell us that protons may be pointing to physics beyond the Standard Model, toward unification, dark matter, or principles we have not yet imagined. Like ancient navigators following stars that hinted at unseen continents, we must follow the Proton's anomalies as guides to the unexplored. But the road back is not only scientific, it is philosophical. To return from the ordeal is to ask what these revelations mean for our conception of reality itself. If the proton is not a fixed entity but a flux, then what does it mean to say that anything exists? Are we built upon foundations or upon processes too turbulent to ever settle? If solidity is an illusion sustained by constant motion, then what does that say about the solidity of the world we touch, the body we inhabit, the universe we trust? The road back forces us to see that real is not a category but a scale. On the human scale, the proton is real enough, stable, enduring, the building block of matter. But on the quantum scale, that solidity dissolves into probabilities and interactions, into fleeting exchanges that have no permanence in themselves. The proton's reality, like our own, depends on perspective. Seen from afar, it is whole. Seen up close, it is storm. This is not contradiction, but duality, a truth that encompasses both sides. As the road winds on, we encounter the echoes of history. Just as atoms were once imagined indivisible and then shattered by discovery, just as quarks were once speculative and then revealed, so too the proton reminds us that knowledge is never final. Every generation thinks it has found the bedrock, only to discover that bedrock crumbles into deeper layers. The road back is the road of humility, the recognition that our maps are always provisional, our truths always temporary, and yet the road is also triumphant. For even in its elusiveness, the proton has given us technologies that shape the modern world. Proton beams and accelerators unlock the secrets of matter. Proton therapy in medicine targets tumors with unprecedented precision. Nuclear reactions in stars powered by protons forge the elements of life. The proton may be mysterious in its essence, but in practice, it sustains the very possibility of life and knowledge. The road back reminds us that mystery and utility are not opposites, they are partners. We thrive on a particle we do not fully understand. The road back also leads us to reflection on ourselves. Humanity too is emergent, less a collection of parts than a pattern in motion. Just as a proton is not defined by its quarks, but by the storm of their interactions, so we are not defined by individual cells or neurons, but by the ceaseless process of life unfolding. The proton is not just a mirror of physics, but a mirror of being. To walk the road back is to bring this lesson home, to see in ourselves the same flux, the same paradox, the same fragile stability. But this road is not without peril. The danger is to retreat into complacency, to treat the proton as good enough, explained, to bury anomalies under convenience. To do so would be to miss the proton's greatest gift, its refusal to settle. The road back demands vigilance, the willingness to follow mystery wherever it leads, even when it threatens to unmake what we thought we knew. For in the end, the road back is not a return to the old world, but a preparation for transformation. We cannot go back to thinking of protons as simple, indivisible particles. We cannot go back to assuming reality is solid, permanent, or straightforward. We return with new eyes, carrying the proton's lessons into every corner of thought.
And as the road narrows, the final challenge emerges, to accept that the proton, in its mystery, is not a weakness of knowledge, but a window into deeper truth. If we can live with its paradoxes, if we can embrace its dualities, then perhaps we are ready for what lies ahead. The resurrection of our understanding, the moment when we see not just the proton, but reality itself in a new light.
But before that resurrection can dawn, we must ask, what kind of truth do we seek? A truth that comforts with simplicity, or a truth that unsettles with depth? The road back demands we choose, and the proton, enigmatic and eternal, waits for our answer. The road back leaves us scarred but wiser, carrying anomalies like burdens and revelations like torches. Yet no journey ends without transformation, and here the arc shifts again, into resurrection. The proton, once thought to be the solid cornerstone of matter, has been broken open, its identity questioned, its very reality suspended in doubt. But now, out of the ordeal and the road back, it must be reborn, not as the particle we imagined, but as something richer, stranger, and ultimately more profound. Resurrection in this context does not mean restoring the proton to its former pedestal. It means accepting that what we thought we knew was an illusion, and that the truth, while unsettling, is infinitely more powerful. To resurrect the proton is to see it no longer as a fixed particle, but as a dynamic nexus of interactions, a perpetual motion of fields and forces that nonetheless presents itself to us as something enduring. This shift is not a loss, it is a gain. It frees us from the prison of simplistic models and immerses us in the reality of nature's depth. Consider the breakthrough of lattice quantum chromodynamics, lattice QCD. For decades, QCD was celebrated for its elegance, but cursed by its complexity. The equations describing quark and gluon interactions could not be solved analytically, leaving the proton shrouded in approximation. Then came the lattice. By discretizing spacetime into a grid and simulating the equations with supercomputers, physicists began to peer into the heart of the proton directly. Out of this computational resurrection emerged images of quark confinement, of flux tubes binding particles together, of energy manifesting as mass. What was once only a theory became visible, tangible, almost palpable in digital form. The proton, reborn through computation, revealed itself as a storm that could be mapped, if not tamed. This resurrection also comes in how we think of stability. For most of human history, stability meant permanence. A stone is stable because it endures. A mountain is stable because it resists change. But the proton teaches a different lesson. Its stability does not come from stasis, but from balance, an eternal equilibrium of chaos. It is not stable because it is simple. It is stable because its internal storm is so finely tuned that it never burns out. The resurrection of the proton is the resurrection of stability itself, no longer a matter of stillness, but of ceaseless motion, held in harmony. The resurrection also reframes reality. If the proton is not a thing, but an emergent pattern, then perhaps all of reality is likewise emergent. What we call objects may only be snapshots of processes, stabilized long enough for us to name them. What we call laws may only be patterns that hold across scales. The proton's rebirth, then, is not just a scientific event, but a metaphysical one. It forces us to abandon the illusion of solidity and embrace the truth of flux, to see reality not as a gallery of objects but as a symphony of becoming. Here lies the deeper resurrection of our relationship to knowledge itself. In the old view, science promised certainty. Atoms were indivisible, protons immutable, reality knowable. The proton's mysteries shattered that promise, but in their place they offered something better: wonder. To resurrect the proton is to resurrect science not as a machine for answers, but as a journey into the infinite, a path that humbles as much as it illuminates. Certainty is replaced by curiosity, and that, paradoxically, is what makes us richer. Yet resurrection is not only philosophical, it is practical. The reborn proton has already transformed the world. Our ability to harness nuclear power, to probe medical mysteries with proton therapy, to build technologies dependent on the strong force, all are fruits of the proton's rebirth in human understanding. And in the future, this resurrection may carry us further still. Insights into proton structure may one day illuminate dark matter or reveal cracks in the standard model that point toward a grander theory. The proton, in refusing to be simple, has become our most powerful ally in the quest for deeper truths. The resurrection also touches the human spirit. In many ways, the proton story is our story. We too are patterns in motion, processes rather than objects. We too find stability not in stasis, but in balance. We too are born, broken, transformed and reborn. The proton's resurrection is a mirror, showing us that identity is not about permanence, but about the capacity to endure change. Just as the proton is not undone by its contradictions, neither are we. But resurrection carries with it a final test: the ability to live with paradox. The proton is both real and not real, both stable and unstable, both particle and process. To resurrect it is not to resolve these contradictions, but to embrace them. The proton is not less real because it is elusive. It is more real because it forces us to expand our definition of reality itself. This, then, is the true resurrection, not of the proton alone, but of our imagination. We are no longer confined to thinking of particles as billiard balls or of matter as solid. We are invited to think bigger, to conceive of reality as a dance of fields, a weave of energies, a storm that gives rise to stars, planets, and consciousness itself. The proton, reborn, is no longer the building block of matter. It is the window through which we glimpse the infinite. And yet resurrection is not an end. It is a threshold. For if the proton is reborn in our understanding, what of the other particles, the other forces, the other mysteries still concealed? If the proton is not what we thought, then how much of reality remains undiscovered, waiting to be resurrected in its turn?
The proton, returned to us transformed, leaves us with a haunting question. If even the foundation of matter must be reimagined, what does that mean for the universe built upon it? And what does it mean for us, creatures who call that universe home? The resurrection is complete, but the journey is far from over.
The resurrection of the proton leaves us with a gift, an elixir distilled not from alchemy, but from decades of collisions, equations, and philosophical reckoning. The elixir is not certainty. Science has abandoned that illusion. It is not closure. The proton remains stubbornly evasive. Instead, the elixir is wisdom, a deeper, subtler way of seeing reality and ourselves, offered by a particle so small we cannot see it, yet so fundamental that without it, we could not exist. This wisdom begins with humility. The proton reminds us that even the most familiar truths may conceal unfathomable complexity. For generations we thought we understood it. 3 quarks in a tidy package, bound by gluons, predictable and stable. But the deeper we looked, the less solid it became. The proton's elixir teaches us that simplicity is often illusion. The world resists reduction. The universe resists final answers. To live with reality is to live with mystery, and to see that mystery not as a failure, but as the essence of truth. Another element of the elixir is interconnectedness. The proton is not a particle in isolation, but a storm of relationships. Quarks entangled with gluons, vacuum fluctuations contributing mass, orbital motions shaping spin. Its identity emerges not from a single part, but from the interplay of all. This mirrors our own condition. A human being is not defined by one cell, one thought, or one moment, but by the web of interactions that constitute a life. The proton's lesson is that reality is not about isolated entities, but about systems, networks, and interdependence. To drink the proton's elixir is to see ourselves as part of this cosmic entanglement, not separate from it. The elixir also sharpens our sense of fragility. If protons were less stable, the universe would collapse. If their interactions were slightly different, stars would not burn, elements would not form, and life would not emerge. Everything we know rests on the knife-edge balance of forces within each proton, and yet inside there is no permanence, only motion, only chaos bound into harmony. The elixir teaches us that existence itself is precarious, sustained by conditions we neither control nor fully understand. To recognize this fragility is not despair, but reverence, a recognition of how miraculous it is that we are here at all. With humility, interconnectedness, and fragility comes courage. For if reality is flux, if even protons are storms rather than stones, then certainty is impossible. But courage allows us to seek nonetheless, to build knowledge not as monuments, but as bridges. The proton's elixir emboldens us to live with ambiguity, to continue searching even when the answers slip through our fingers. It reminds us that science is not about possessing truth, but about pursuing it, a pursuit that is endless yet essential. There is a darker note to the elixir as well, the reminder of ignorance. The proton remains unsolved. Its spin puzzle, its radius discrepancy, its emergent mass, all defy full explanation. And beyond the proton lie even greater mysteries: dark matter, dark energy, unification, the quantum structure of space-time. The elixir forces us to acknowledge that our knowledge, vast though it seems, is but a flicker in a vast darkness. This is not a weakness, but a challenge. Ignorance is not the absence of knowledge, but the horizon of discovery. And yet, perhaps the most profound gift of the proton's elixir is wonder, for in its contradictions, in its evasions, in its paradoxes, the proton reveals a cosmos more beautiful than any tidy model could convey. It is not disappointing that the proton resists simplification. It is exhilarating. It means reality is richer than we can imagine, deeper than we can map, stranger than we can define. To live in such a universe is to live in poetry as much as in physics. The proton's elixir awakens awe, the sense that even the smallest thing contains infinity. What then do we do with this elixir? We carry it back into the ordinary world. We let it shape how we see matter, how we see life, how we see ourselves. We teach students not just the equations of protons, but the mysteries they conceal. We remind ourselves in moments of arrogance that even our own bodies are built on foundations we cannot fully explain. We live with the recognition that the universe is not ours to master, but ours to marvel at. The return with the elixir does not resolve the proton's mystery, it spreads it. It tells us that reality is not less real because it is elusive, but more real because it compels us to stretch our minds, to expand our categories, to redefine what real means. The elixir is transformation, the understanding that uncertainty is not a flaw, but the doorway to wisdom. And yet, even as we return with this gift, we cannot help but ask, what other elixirs wait to be uncovered? If the proton conceals such truths, what about the neutron, the neutrino, the photon? What about the forces we have not yet discovered, the dimensions we cannot yet perceive? The proton's elixir is not the end of the story, but the beginning of many others. We return changed, but not finished. For the proton's final gift is a challenge to keep seeking, to keep questioning, to never mistake partial knowledge for complete truth. And in this challenge lies the greatest elixir of all, the inexhaustible wonder of a universe that is always more than it seems. But now, as the elixir settles, another trial approaches. For wisdom alone is not enough. The proton's mystery invites interpretation, and interpretations can divide, distort, or enlighten. The return is not final. It leads into trials of meaning. And so we ask, what does this elixir truly mean, and how shall we use it? The elixir has been won. We have returned from the ordeal with wisdom in hand, a deeper appreciation for the proton's mystery, its fragility, its emergent nature, and its awe-inspiring role in binding reality together. Yet every elixir invites not just gratitude, but interpretation. And here lies the next challenge, to make sense of what we have learned, to wrestle with meaning itself. For knowledge is not neutral, it must be framed, debated, and applied. And the interpretations of the proton's truth are as varied, as contentious, and as revealing as the proton itself. The first trial is the scientific one. Within physics, the proton has become a battleground of models, each vying to account for its anomalies. Quantum chromodynamics, our reigning theory, insists that all is explainable through quarks and gluons. Though the math is so complex, we rely on approximations and simulations. Others whisper of new physics, hidden forces, undiscovered symmetries, exotic particles that could explain why the proton's radius shifts or why its spin refuses to align with expectations. In these debates, each interpretation carries implications that ripple outward. If QCD alone is sufficient, then the proton is a triumph of known science. If new physics is required, then the proton is a crack in the standard model's veneer, a clue pointing to deeper, undiscovered truths. But there are trials beyond science too. Philosophers of science confront the proton as a mirror of epistemology itself. What does it mean to say something is real if our models cannot capture it fully? Is reality a property of the proton itself, or of the frameworks we impose upon it? Some argue that protons, like quarks or gluons, are theoretical constructs, useful fictions that allow us to organize experience but do not exist independently. Others counter that protons must be real, for we measure their effects directly. The mass of the Earth, the glow of stars, the solidity of matter all depend on their existence. The trial here is not about data, but about language, whether our words, particle, mass, spin, are windows into truth or merely scaffolds around mystery. Then comes the cultural interpretation. In the wider world, protons have become symbols. For some, they are the ultimate evidence of science's mastery over nature, proof that humanity can probe the very heart of matter. For others, they are evidence of humility, of limits we cannot surpass, of mysteries that remind us of our smallness. The way we speak of protons shapes how we see ourselves, as conquerors of knowledge or as pilgrims wandering a boundless universe. And lurking beneath these interpretations is the oldest trial of all, the human longing for meaning. The proton, after all, is not just a puzzle, it is us. Every atom in our bodies, every star in the sky, every breath we take is stitched together by protons. To confront their mystery is to confront the fragility of our own existence. Are we built on certainty or on flux? Are we grounded in permanence or suspended in paradox? Each interpretation of the proton's nature doubles as an interpretation of our own. The trials of interpretation also reveal tensions between reductionism and holism. Reductionists argue that the proton can and will be explained by drilling ever deeper into its components. Better simulations, higher energy collisions, more precise measurements. Holists counter that the proton is not reducible to parts, that its essence lies in emergence, in the collective dance of quarks and gluons, inseparable from the context of the whole. These two visions, atomistic versus systemic, reflect broader divides in how we interpret reality itself. Do we explain life, consciousness, and the cosmos by reducing them to particles, or by embracing the emergent properties of systems? The proton becomes the test case for this philosophical battle. The trials are not purely intellectual, they carry practical consequences. If our interpretations lean too heavily on certainty, we risk dogmatism, clinging to models that may one day prove incomplete. If we lean too far into mystery, we risk paralysis, marveling at complexity without advancing understanding. The challenge is to walk between, to interpret the proton as real enough to build upon, yet mysterious enough to keep us humble. In all these trials, one lesson emerges. Interpretation is itself part of reality. The proton is not simply a particle awaiting discovery. It is an event in consciousness, a point where human perception collides with cosmic truth. Every experiment, every debate, every philosophical reflection is part of the proton's story. The trials of interpretation remind us that science is not separate from humanity, but is one of its deepest expressions. And as these interpretations swirl, scientific, philosophical, cultural, existential, we begin to sense that the proton's gift is larger than itself. It is not only a particle but a prism, refracting our questions back to us in unexpected colors. The proton's mystery forces us to confront what it means to know, to believe, to be. But these trials, though demanding, are not the final stage. Beyond them lies something greater, the ultimate boon, the synthesis that unifies science and philosophy, particle and process, human and cosmos. It is the moment where the proton stops being only a puzzle and becomes a revelation, a lens through which we glimpse the unity of all things, and that at last is what waits ahead. The trials of interpretation are fierce, but if endured, they deliver a prize greater than answers, a vision. This is the ultimate boon, the moment when the proton ceases to be merely an object of study and becomes a symbol, a revelation, a bridge between science and philosophy. The boon is not a solved equation or a completed model. It is the recognition that reality, at its deepest level, is both stranger and more coherent than we ever imagined. What then does the proton teach us? First, it teaches us about unity. The proton contains contradictions, quarks bound yet confined, gluons both carriers and participants, mass emerging from motion rather than substance. Yet out of this turbulence comes stability. Out of chaos comes permanence. The proton shows us that unity does not mean simplicity. It means balance. In its ceaseless churn, the proton achieves harmony, a harmony robust enough to endure for billions of years, stable enough to build stars, planets, and life. This is the boon, a model of existence in which conflict and contradiction are not flaws, but foundations. Second, the proton teaches us humility. Its mysteries remind us that our knowledge is provisional, our models incomplete. We believed for centuries that matter was simple, only to learn that its foundations are beyond our full grasp. And yet in this humility lies strength, for science thrives not on certainty, but on doubt. The proton's resistance to complete understanding ensures that inquiry continues, that imagination expands, that discovery never ceases. This too is the boon, the awareness that mystery itself is the lifeblood of knowledge. Third, the proton teaches us connection. It is not alone but entangled with the cosmos. The proton's properties dictate the chemistry of elements, the life cycles of stars, the formation of galaxies. Its stability allows for time, its fragility allows for change. Each of us is not merely made of protons. We are echoes of the same processes that give them form. In this sense, the proton's lesson is that we are not separate from the universe, but woven into its fabric. The smallest particle reflects the largest whole. The microcosm and the macrocosm are one. But the boon has an even deeper dimension. It redefines reality itself. For the proton's contradictions force us to abandon the notion that reality is composed of things. Instead, reality appears as relationships, interactions, processes. The proton is not a particle so much as a knot in the cosmic weave, a convergence of fields, a rhythm of probabilities. If the proton is real, it is real in the way a storm is real, not as a static object, but as a dynamic pattern, a temporary stability in a sea of change. This revelation extends beyond physics. It touches philosophy, spirituality, even the human experience. Just as the proton is not reducible to its quarks, so a human being is not reducible to cells or genes. Just as the proton's mass arises from motion, so meaning arises not from parts, but from the whole. The boon whispers that reality is emergent, that existence itself is an unfolding symphony, and that we, like protons, are not things but processes, not objects but stories in motion. To receive this boon is to be transformed. Once we thought of protons as bricks in a cosmic wall. Now we see them as windows into the infinite. Once we thought solidity was permanent. Now we know solidity is illusion, stability born of flux. Once we thought science was about answers. Now we see it is about questions, about living in wonder. And yet, as with all boons, the gift is double-edged. For with the revelation comes responsibility. If the proton is a process, then so is everything we build upon it. Our lives, our civilizations, our truths, they are all provisional, all emergent, all fragile. The boon does not give us certainty. It gives us awareness of impermanence. But this awareness is not despair. It is liberation. To know that everything is flux is to know that everything is possibility. The proton, then, is both foundation and frontier. It grounds us in the stability of matter, yet it opens us to the instability of meaning. It assures us that we are real enough to exist, yet reminds us that reality is never finished. It holds us steady while pushing us forward. This paradox is the ultimate boon. To hold it is to see the universe anew. The proton is not a problem to solve, but a story to live with, a reminder that the smallest things contain the largest truths, and that the deepest mysteries are not barriers but gateways. In its hidden storm, the proton reveals the unity of all things, matter and energy, chaos and order, science and philosophy, the cosmos and ourselves. And yet, even as we receive this gift, a final task remains. For no boon is complete until it is carried back, until the hero returns to the ordinary world transformed. The question is, how do we live with the knowledge that even protons are processes, that reality itself is emergent, fragile, and strange? Can we integrate this wisdom into our lives, our sciences, our sense of self? This, then, is the road to the final equilibrium. To carry the boon not as abstract wonder, but as living truth, shaping how we see the world and how we live within it. And so we ask, if protons are not what we thought, then what are we? The answer waits in the final steps of the journey. The journey began with certainty. We thought protons were the indivisible heart of matter, the stable anchors of the universe. We believed they were simple, permanent, and fully real. Along the way, certainty cracked. Spin refused to add up, radii disagreed, and mass emerged not from substance but from storm. We descended into confusion, wrestled with paradox, and emerged with a boon, not certainty but wisdom. And now, at last, we arrive at the new equilibrium, the transformation of perspective, the integration of truth into life. This new equilibrium does not return us to the world we left. It cannot. We cannot look at protons or reality itself as we once did. Instead, we live in a world where solidity is illusion, stability is motion, and reality is emergence. To live here is to embrace paradox, to walk with mystery, to accept that knowledge is never final but always unfolding. The proton becomes our teacher. It tells us that stability is not the absence of change, but the perfect balance of it. Inside every proton is a maelstrom, quarks bound by gluons interacting with themselves, virtual particles flaring in and out of existence. And yet, this chaos does not dissolve into nothing. It coheres, it sustains, it endures for billions of years. From this, we learn that permanence is not about resisting change, but about embodying it. Our own lives, like protons, are not static objects, but storms held together by balance. The equilibrium is not stasis, it is harmony. The new equilibrium also reshapes how we think of reality. Once we imagined the universe as built from parts, particles, atoms, building blocks. Now we see that there are no true parts, only processes, only relationships. The proton is not a thing but a knot of interactions, a pattern in motion. If protons are real, they are real the way rivers are real, always flowing, never the same, yet enduring as form. To live in this equilibrium is to see reality not as a gallery of objects, but as a dance of patterns. This shift reverberates into philosophy. If the foundation of matter is flux, then so is the foundation of meaning. Truth is not an absolute carved in stone, but an emergent property of context, coherence, and relationship. Certainty fades, but wisdom grows. Just as the proton resists final definition, so do we. To live with this is not weakness, but freedom. We are not bound to illusions of permanence. We are free to adapt, to change, to create. The equilibrium also redefines science itself. For centuries, we sought closure, the final theory, the ultimate equation, the last word. The proton reveals that closure is an illusion. Knowledge is not an endpoint, but a horizon, always receding, always inviting us further. This does not diminish science, it ennobles it. To be a scientist is not to conquer mystery, but to live in relationship with it, to chart the unknown without ever exhausting it. The proton's lesson is that the unknown is not a failure, but a gift, the inexhaustible wellspring of discovery. For humanity, the new equilibrium offers both awe and responsibility. Awe because we are built from storms we cannot fully explain, woven from mysteries that sustain us without our consent. Responsibility because knowing this fragility should humble us. If the proton's balance faltered even slightly, the universe would collapse. The stars would not shine. The earth would not exist. Life would never have arisen. Everything we are is contingent, dependent on processes deeper than our comprehension. To live in this equilibrium is to live with gratitude, aware of how precarious and precious existence truly is. The new equilibrium also carries ethical weight. If we are processes like protons, emergent, interconnected, fragile, then how should we live? We cannot pretend to be isolated, self-contained entities. We are bound together, each life a pattern in the larger storm of humanity, each generation an echo of cosmic processes. To live as if we are separate is illusion. To live as if we are connected is truth. The proton teaches us that survival comes not from stasis but from harmony. Perhaps we too will endure only if we can balance our chaos into coherence. And there is one final lesson in this new equilibrium, the redefinition of real. For centuries, reality meant solidity, permanence, tangibility. Protons have stripped that illusion away. They're not real in that sense. They are real in a deeper one. They are real because they endure, not as objects but as processes. They are real because they sustain, not by resisting change but by embracing it. They are real because they reveal that the universe is not a collection of things but a symphony of becoming. To live with this equilibrium is to embrace a new definition of reality, not fixed but flowing. The seeker, having traveled the circle, returns home, but home is changed because the seeker is changed. We began with protons as bricks. We return with protons as storms. We began with certainty. We return with wonder. We began with solidity. We return with flux.
This is the new equilibrium. Not the end of the story, but the beginning of a new way of seeing. A world where the smallest things are infinite, where the simplest questions are bottomless, where the proton is not just a particle but a philosophy.
Yet even as we settle into this equilibrium, one question lingers. If even the proton resists finality, then what else in the universe waits to be transformed? There is a silence at the end of every great journey. When the hero returns, when the trials are behind them, when the elixir has been delivered, there is a stillness, a chance to breathe, to look back at what has been endured, and to ask what it all means. For us, the silence comes now, at the end of our descent into the proton. What have we learned? That the proton, once thought simple, is a labyrinth. That inside its boundaries lie storms of quarks and gluons, their dances creating mass, spin, and stability. That its solidity is illusion, its permanence precarious, its identity emergent. That it is less a thing than a process, less a foundation than a song sustained across billions of years. We thought we were built upon bricks. We now know we are built upon patterns. But the silence deepens when we realize that this truth does not diminish the proton, it elevates it. The very fact that it resists definition, that it defies simplicity, that it humbles our equations and confounds our instruments, that is what makes it real. Real not in the sense of permanence, but in the sense of endurance. Real not because we can grasp it, but because we cannot exhaust it. The proton is real because it forces us to expand what real means. And in this expansion lies the haunting gift. If the proton is not an object but a process, then so are we. If the proton endures not by resisting chaos, but by balancing it, then so must we. If the proton is a storm that holds together long enough to build a universe, then perhaps we too are storms, brief, fragile, and yet capable of creating meaning, life, and memory. The silence becomes a mirror. We look at the proton and see ourselves, impermanent yet enduring, fragile yet powerful, fleeting yet real. Its contradictions are ours, its mystery is ours, its balance is ours. And so the journey ends, not with certainty, but with a question that echoes into eternity. If even the smallest particle, the proton, is not what it seems, then what of the universe built upon it? What of time, of space, of life, of us? Perhaps reality itself is not a collection of answers, but a cascade of questions, each leading deeper, each demanding more. Perhaps to exist is not to stand on foundations, but to flow in storms. Perhaps we are not the masters of reality, but its reflections, its echoes, its fleeting sparks. The proton endures. It holds the stars together. It holds our atoms. It holds the world. And yet in its storm, it whispers a final truth. Nothing is solid. Nothing is final. Nothing is ever fully real in the way we once believed. And so, in the silence, we are left with wonder. Not the question, are protons real, but the deeper one, the one that lingers after the last word fades. If reality itself is a storm, what else waits to be revealed?
Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.